in this slide, we want to speak about well-ordering principle and how we can use well-ordering principle in proving some theorems. The well-ordering principle says that every non-empty set of integers whose elements are greater than some real number, such set has the smallest element. In other words, if we have S is a set of integers and satisfy two conditions. First, it is non-empty. Second, we can find some real number such that any element in S is greater than this real number. Then we can find a smallest element in S. That means I can find an element in S such that any integer in S is greater than this number. Let's discuss in this example how we can use well-ordering principle. So the question in this example, which of the following sets of integer has the smallest element? The first one is the set of all prime numbers greater than 8, and the second one is the set of positive real numbers. The first set here is a subset of integers, and it is bounded by 8, and the set of prime numbers, of course, greater than 8 is non-empty. So it satisfies for me all the conditions of well-ordering principle. So we can conclude that this set have a smallest element by using well-ordering principle. The second one is bounded by below from by 0, and of course it's non-empty, but it's not a subset of R. It's not the set of integers, and so I cannot use well-ordering principle. So in the solution, I can say that the first set, the set of all prime numbers greater than 8, it has the smallest element by using well-ordering principle. And of course, you know what is the answer, because this set is very easy to describe, and the smallest element is supposed to be 11. Okay, and the second one, it doesn't satisfy for me the conditions that to be a subset of integers, and actually we can prove that by contradiction. If R is the smallest element greater than 0, then R over 2 is also greater than 0, and it will be less than R. So we cannot have a smallest element. Before we speak about examples, how to use well-ordering principle in proving some statements, we have also a version of a well-ordering principle for natural numbers. And it says that every non-empty subset of the natural numbers has the smallest element. This is simpler than the well-ordering principle for integers. And the reason is because the set here is a subset of natural numbers. That means it is already bounded from below by 0. And that's why I just need two conditions here. So if we have S is a subset of natural numbers, I need only to check that S is non-empty. Okay, then we have, by well-ordering principle, we will have the smallest element. Use this in this example. So we are going to use well-ordering principle with a direct proof. And in this example, we have A and B are non-zero integers. Then we want to prove that there is a smallest positive linear combination of A and B. So that means what? That means when we find this smallest positive linear combination, any linear combination will give me a number greater than this number, the smallest one. The proof is direct proof, so we let a and b be non-zero integers. And I will define my set S to be the set of all positive linear combination on a and b. So we want to prove that this S or linear combination have a smallest element. This is a statement of the example. But then from my definition, S is greater than 0. That means, because we said all positive linear combination, that means S is a subset of natural numbers. Now to use the well-ordering principle, I need only to check that this S is not empty. So I can argue that S is not empty. Why? Because we know that A is an integer and it's not 0. So we have two choices. Either A is greater than 0, then A itself is the linear combination of A and B, and it will be in S. Otherwise, A will be less than 0, and in this case I can have minus A will be positive, and it is also a linear combination of A and B. So in both cases tells me that S is non-empty. Now S is a subset of integers and S is non-empty. By well-ordering principle, the set S will have a smallest element. We denote this element by R. Thus by definition, R will be the smallest positive linear combination of A and B, and this ends my solution. We see in this example that the well-ordering principle is a very powerful tool, because when you give me A and B integers, actually I didn't tell you how you can construct this smallest positive linear combination. I know that it exists by using well-ordering principle. So what we have here, we have an existence problem. Existence statement, and the proof we give here is not a constructive proof. So I didn't tell you how you can construct this smallest positive linear combination, but by well-ordering principle, we know that it exists, this number, and that's enough for my proof to prove this statement. Let's look to another example where we will use well-ordering principle with a proof by contradiction. In this example, we want to prove that every natural number greater than 1 is prime or is a product of primes. So we know that any natural number greater than 1 is prime or composite. So we want to prove that can be written, even the composite can be written as a product of primes. The statements seems a trivial statement, but still we wanted to use our tools to prove this statement. For the proof by contradiction, my assumption will be, we assume there is a natural number greater than 1, which is not prime, and it is not a product of primes. So with this assumption here of contradiction, I can define this set T, okay, which contains all such numbers. That means T contains numbers which are not prime and it's not a product of primes. Okay. Now this set T is not empty by my assumption. So by well-ordered principle, we have T is a subset of natural numbers and it's not empty. Then T contains the smallest number. We denote it here by M. Now by definition of the set T, M is not a prime and M is greater than 1. That means M is a composite. That means what? It means that we can write M as a product of S, R, and R, where S is greater than 1 and less than M, and R is greater than 1 and less than M. But this means that R and S are not in the set T because they are smaller than M. That means S and R are prime, or they are product of primes, because the set T is a set of all integers which are not prime and not a product of primes. But then M will be the product of S and R, so since any of them is a prime or is a product of primes, that means M itself is a product of primes. And this gives me a contradiction. Since from our proof, we select M to be in T, and T are the numbers which are not product of primes, and then we found again that M is a product of primes, and this is my contradiction. Therefore, my assumption is wrong, and that means every natural number greater than 1 is a prime or is a product of primes. Now, using well-ordering principle, we can also prove a very powerful theorem, the division algorithm. And it says that if you have A and B are integers, where A is positive, then you can find a unique Q and R such that this number B is equal to the product of A multiplied with Q plus R. And this uniqueness under the condition that R is supposed to be less than A and greater than or equal to 0. A is always called the divisor, and Q found the unique Q is for every B. You can find a Q, and this Q is called the quotient. And the number R is the remainder. Let me explain for you what this means in examples. So let's, for example, take A is equal to 7, and for this 7, which is greater than 1, let's take B is equal to 25, which will be written as, using the divisor 7, can be written as 7 multiplied with 3 plus 4. And the theorem tells me that this 3 and this 4 are unique. If I take, for example, another one, which is 28, for example, it will be 7 multiplied with 4 plus 0 is unique. These 4 and 0 are unique because we have here the remainder have to be less than 7 and greater than or equal to 0. Now, if I write my B can be negative, so I can take minus 25, and then normally students write this as 7 multiplied with minus 3 minus 4. But here minus 4 is not what the theorem tells me. It tells me that the remainder always, all this number have to be positive. And to do that, I have to write it in a different way. So it will be 7 multiplied with minus 4. And this gives me a 28. And then I add 3. This is the remainder of dividing minus 25 by 7. And minus 4 will be the quotient. Now we have examples in our mind and we understand the statement. Let's see how we prove it. So notice that the statement we have here is unique extension statement, and that means the proof is divided to two parts. First, the existence and then uniqueness. And for the existence, we'll use the well-ordering principle. So for the existence, I will define the following set. We take the set S of all combination of the form b minus ak, where k is an integer, and we want also b minus ak to be greater than or equal to 0. So the numbers here are, all of them are integers, and all of them are greater than or equal to 0. So I want to use the well-ordering principle for integers. The only conditions remain for me is to prove that this set S is non-empty. Note that if b is greater than or equal to 0, then we can write b as then b minus 0a is a combination, and it's greater than or equal to 0, so it belongs to S. And if b is negative, then b minus 2ba will be equal to b multiplied by 1 minus 2a. Now from the definition of A, this will be negative, and since b also is negative, all of them will be positive. So this element in the form of the elements in S, and it belongs to S. So we see that we can show that S is non-empty. So my set S satisfies all the conditions for the well-ordering principle. So that means what? That means we can find the smallest element, and this element I denoted by R, and it will be the number we are looking for, the remainder. Okay, and since R belongs to S, that means it is in this form. So we can find the existing integer q, and this q is equal to, such that R is equal to b minus aq. So this gives me that b is equal to aq plus r, and this gives me an existence. So I prove the existence, but then it remains for me, is this R satisfies the conditions, because I want R to be less than a and greater than or equal to 0. Of course, from the definition of S, we know that R is greater than or equal to 0. But is R less than A? So to prove that R is less than A, I will use proof by contradiction and assume that R is greater than or equal to A. But this means that R minus A is greater than or equal to 0, and also R minus A is less than or equal to R. But using the definition of R here, we can write also R minus A as B minus A multiplied with Q plus 1. That means what? This means that R minus A actually is in the set S we defined before here. And it means also that R is just not the smallest element in S. Yeah, R minus A has the same combination b minus A and a number in the and an integer multiplied with an integer. So it is an element in S and it is less than R. This gives me a contradiction. By our choice, R is supposed to be the smallest element in R. This proves the existence statement. Now we have to prove the uniqueness. So for the uniqueness, we assume that we can write B in two different ways. A multiplied with Q1 plus R1, and A multiplied Q2 plus R2. Where this satisfies for me the conditions. All of them are integers, and R1 and R2 are less than A and greater than or equal to 0. Without loss of generality, we can also assume that R1 is less than R2, less than or equal to R2. Then using algebraic manipulation, R2 minus R1 is equal to A Q1 minus Q2. And this means that A divides R2 minus R1. However, R2 minus R1 is less than A because both of them are less than A, so the difference will be also less than A. And from this assumption, R2 minus R1 is greater than equal to 0. But now A divides R2 minus R1 and R2 minus R1 is less than A. This forces that R2 minus R1 is equal to 0. Substitute this value R2 minus R1 equal to 0 here. We will find that 0 is equal to A multiplied with Q1 minus Q2. Since A is not 0, that means Q1 minus Q2 is equal to 0. These two equations R2 minus R1 is equal to 0 and Q1 minus Q2 is equal to 0. It means that R1 is equal to R2 and Q1 is equal to Q2. And this proves the uniqueness. Whenever you write B in this form, that means you have a unique Q and a unique R. And this ends this slide about well-ordering principle.